name is Fabrizia, and today I will talk about our approach on how to visualize anomalies in energy flow. So when you drive a car, you're not aware of all the components that work together, but until all these components work smoothly, they undergo many cycles of adaptation and fine-tuning. And since it's not really realistic to build a car for every change you do on a component of this car, it's common to do simulations, simulation test drives, and they generate time series for each component for different types of parameters. We focus on energy flow, so that can be heat flow or pressure or something like that between two components. And since a simulation can be very long, looking through all this data is a very tedious and long process. And now we work with industry partners, and they use a software, AVL Cruise, which you can see a picture here. It's kind of like a network of all the components and the energy flowing between these components. And it's like an animation, basically like a video showing the amount of energy at each time, each point in time. And the current system they use is lacking. They can only watch the animation in a linear manner. They can barely interact with it. It has very limited information. It just shows the current value and no abstractions and so on. And so they desired a tool which is more interactive and which guides them in their analysis process a little bit more. So the requirements are for this new software. It should support detecting of important incidents. So we perform automatic anomaly analysis and calculate statistics. It should be independent of the underlying structure of the components of the car system, and it should improve the visuals. So you saw in the picture, it does not give a lot of information. So they want more, extract more knowledge from same space, basically. And they also wanted to have more user interaction. So we provide multiple playback options. And all in all, the system should be platform independent, so we decided on a web application. We implemented a server-client structure. The client gives a request to the server. The server, we implemented a Python Flask server. It handles the model acquisition, data analysis, and data queries, and once it's finished, it stuffs all the data into a JSON file, sends it back to the client, and the client then takes the data and forms the visualization and also the user interaction. And we did a web client using JavaScript and D3.js for the visualization. So before we can actually visualize something, we need to have a basic structure of the underlying model of the system. We have a system is composed of components, and each component can be, for example, the engine or the heater or something. Each component has inlet ports and outlet ports where the energy comes and goes, and components are connected by outlet ports and an inlet port. So you can see here a component connected to a second component, and in between energy flows. As I mentioned before, that can be like heat or pressure or something like that. Once we have this model, we can then analyze the time series. So each component has a time series associated to it from the simulation. We calculate different types of statistics, like the mean or standard. And then we perform anomaly detection on this time series. And finally, we put all this data into a structure which is which can be easily queried. For example, select different flows or select different parameters. So the anomaly detection basically marks each time or each frame or each value in the time series as anomalous or not anomalous. And for now, we implemented 3 different approaches. The isolation forest, which is an unsupervised method, which kind of builds a tree structure, and depending on where the leaf in this tree structure is, it's marked as anomalous or not. The min-max threshold is very basic. It just marks all the points over certain percentile as anomalous or over or under. And the modified set score is it calculates the amount of standard deviations a value is far away from the median. So these are the 3 types of anomaly detections we performed for now. We can kind of exchange them for any other. So once we have all the data we need, we send it to the client and put together our visualization. So you can see a screenshot of such a visualization. We have 4 main views. The simulation player, you can see the big one in the middle, the anomaly timeline here on the bottom, and then we have the data labels. Like you see here these small cartlets associated to each flow, or each active flow which has data. And finally, the parameter table, which gives global information of the global parameter set for this simulation. So the simulation player is all in all very similar to the software the engineers used before. So we see the network of the components of the underlying system, and in between the flows. And it shows the state of the system at a specific time point. And so the value of each flow is depicted in the thickness of the connections of the flows. And the direction of the flow we can see by these arrows on the flows, like here, for example. And we decided to continue the thickness because you can very quickly grasp that, okay, for example, here between the engine and the torque converter, there is a lot of energy flowing, and between the torque converter and the speed gearbox, there's a lot less. So you can very quickly grasp the differences between the energy flow at a specific point in time. And additionally, each flow has these data labels. I will talk more about these later. And then we have the anomaly timeline. So as we performed the anomaly detection analysis, we have over our whole simulation points in time where there is something occurred in the simulation. And basically, engineers are interested in these points. So we aligned them in a linear manner from 0 to the end of the simulation. So like 3,000, 9,000 points, whatever. And each row is dedicated to each type of anomaly we calculated. So here you see in the first row the isolation forest, the min-max, and the modified set score in the last. At first, we have a summary of this timeline. So it gives an overview of the whole system state. So kind of like all components combined. But this only tells us that something happened, but not where it happened. So we have the option to add components to this timeline. And then you see on the bottom, the summary timeline gets shrunk on the bottom. And on top, we have a detailed view of a window of the component we are interested in. So you see here this small orange rectangle. It shows this is the window frame that we are looking at. So it's kind of, we call it the zoom window. And you can move this and change the size of the window. And yeah, so you can select components and navigate throughout this timeline. So you can also directly select the anomaly point and jump directly to this point in the simulation. Then we have the data label. As I mentioned before, it's each component is associated with one data label or one the flow underneath. And it gives more information on the specific component. So for one, we have the actual value of the simulation of the flow. In the first level, we have 4 different levels of detail, and the user can choose how much detail he wants to look at. So first we have only the scalar value, the actual value, then we can increase it and we get a sparkline. So it's basically just a line graph of the evolution of the flow for this component. And on the third level, we add the anomaly timeline. It's kind of like the big timeline, but just for this one component. And finally, we can increase one more level and we get a zoomed window of the sparkline. The zoom window corresponds to the zoom window of the timeline. And since these are very small and sometimes we want to investigate one component in more detail, we can expand this view of one of these data labels to span basically the whole screen, and we get more detail. This is a little bit of work in progress, so we plan to add more detailed visualizations to this view still. The parameter table is basically just gives an indication of the global parameter set for this one, and it's more of a view that's for future work where we want to visualize not only a single one but multiple ones at once, and where we can have a summary of these selected parameters and select subsets and brush the data with this. And finally, as I mentioned before, we have more user interaction or more playback. So we have the normal play mode where the visualization just runs kind of like a video. And we can also use the fast forward option where it speeds up until a point in time where it hits an anomaly. Then it slows down so that the user can inspect the anomaly or the visualization, the data in more detail at this point. And we can also navigate frame by frame, so we can move one frame forward or backwards and so on. And as I mentioned before, we can jump directly to a point in time by selecting an anomaly in the timeline. And we can change the amount of information we want to depict by adding a component to the timeline or by expanding the data label. And if we have a little bit of time left, I will show a short video of how that looks in real life. This is the anomaly timeline. So we can add components, then it gets added to the bottom here, and we can see the zoomed version of the anomaly of a specific component. We also can delete it. Yeah, I did not mention this yet. If we touch an anomaly point in the zoomed version, we can have a visual context of the component which it is associated to. And we can move the window and select timeline, select a point in time directly. And yeah, here you can see how it affects the zoom. So you see how quickly it changes from overview to more detail. The data label, you can set the detail, the level of detail which you want, so you can increase it, you can decrease it, and you can also select the big view, or like the details view. And here you can also choose the level of detail you want to have depicted. And if we move the timeline or change the zoom window, you can also see the reference in the data label. And here's a short video of how user interaction could work. So we have the basic play. You can see how how the value changes for each flow. And you can quickly see the differences between the single flows. And the fast forward, it moves quickly until it hits an anomaly, and then it's slow again. Fast, and now it's hitting again, so it slows down, and once it's over, it speeds up again. Or you can, as I mentioned, navigate frame by frame, increase the frame, decrease the frame, so you can really precisely select a specific frame if you want. And yeah, for future work, I mentioned before we want to expand the details data label a little bit more, and here you can see how this was a first approach to our work. At first we wanted to visualize the samples of such simulations, but turned out it was a bit too much work, so we focused on single view, and this is how it can look once we have the multi-view implemented. So you can see a summary of all the runs, and you can select subsets and brush the data and so on. And that's it. So if you have any questions, please feel free to ask.
Thank you very much. We have time for a couple of questions, yeah?
What technology do you use to draw the visualization?
Sorry?
What technology do you use to draw the visualization?
We use JavaScript for the general processing and D3.js for the actual drawing.
Okay, thank you.
Start there.
Thank you for your talk. The tool seems very informative for the engineers, but on the same time it increases complexity, I think. How did the engineers react to that?
I had a bit of technical problems, so we did not come to the point yet where we can actually test it with the engineers. But the first feedback we got from them was very positive, so they liked that they have more interaction and more information available. And you can set the level of information you want, so you can also just go back basically to the previous animation, where you just have the kind of like a video, so they can basically choose how much the interaction they want and how much information.
Yeah, you know, I had the same question, so I don't know, people are just taking my questions today. But I think it's absolutely crucial that you ask like engineers at some point, and then you, I mean, this work has a potential to be used in practice and also maybe published at a conference, but evaluation by engineers is necessary and probably difficult because they also, I mean, to make it like, you know, kind of evaluation study is also like a complicated task.
Yeah.
You know,
so this is on our to-do list.
Thank you.
One question is, does the arrangement of the components that are connected on the canvas, does this arrangement have any meaning, that the spatial relation? Because it looked rather chaotic.
Yeah, so basically no, but you can, the user can drag the components around and set them how they want it to be. we have a very basic graph layout algorithm implemented, which sets a first layout, but it's really not very good. So this is definitely work we can improve, the layouting itself, but for now we focus more on the actual visualization and how to represent the data. But yeah, this is still something we need to improve.
Okay, thank you.
So this is a more or less software development question. I have a bit of experience in 3.3GS, and it was a difficult process. So how long did it take to implement this incredible tool, and what was your experience?
Please don't ask.
Oh no.
D3GS can be very tricky, so I've spent hours to just align something. And it's very powerful, and you can do a lot of incredible things, but until you reach the point where you want it to look how you want it to look, it can take a lot of time.
I see. Thank you. Really interesting.
Anybody else? Maybe I just have a quick question. There was this anomaly timeline. Can you quickly go to that slide? So yeah, does this mean that the third metric, there was anomaly all the time?
Yeah, this is actually a really bad example. Good that you caught it. Here it actually looks like there is an anomaly everywhere, but if you expand the data labels and you see for each component, you see that it's not everywhere, but in summary, yeah, it's detected a anomaly everywhere, yeah.
Mm-hmm. Okay, thank you.
This is also one of the reasons why we implemented 3 different types of anomaly detection, because they all detect different things, and we don't know yet really which is the perfect one.
Mm-hmm. Okay, thank you. Yeah, if there are no further questions, let's thank the speaker again. Thank you very much.